Okay, hello folks. Welcome to another week of Offsite Learning. This week we're going to be wrapping up chapter 13. So that starts with lenses. So you will need this note booklet from the Google Classroom. Okay, it's just a continuation from where we left off. You can see it even starts on page 35 because normally it would just be one big booklet. Okay, let's jump in. Okay, so just a heads up at the beginning here, kind of going to treat this a bit differently. I'm going to split this topic kind of into two. So first I'll just do kind of the theory and an introduction to lenses, specifically converging lenses. And then in another video, I'll kind of go through some of the examples and stuff so that if you're just wanting an intro and overview and then you're ready to go try the assignment, that's great, you can do that, okay? But if you're wanting to see me work through a few, well, then you'll have that other video that you can go to, or any combination of the two. You might want to get a little bit of background and then go just see examples, or maybe you just want examples. But this will serve as the intro to lenses. So lenses in some sense work the same way as mirrors, right? They work by changing the direction that light is going to travel. It's just that with mirrors, they work through reflection, right? With lenses, they're going to work through refraction. So what is a lens? It's just a piece of material with a higher refractive index than air, so that when light goes through it, it gets bent. Okay, so there are two main types, just like there were two main types of mirrors, well, three if you count plane mirrors, but for lenses, there's going to be converging and diverging. You may notice the shapes there are kind of switched. What was a converging mirror was a concave mirror, but now a converging lens is a convex lens. This concave shape, when we were talking about mirrors, that was a converging mirror. Now it's a diverging lens. We'll see why when we look at how rays behave when they encounter a surface like this. Just a note off the top, we're going to assume these lenses are thin. So we'll assume the lenses are thin. Okay, it just makes analysis more practical. Okay, and realistically, a lot of lenses are pretty thin and thin enough that this actually that what we are going to do approximates pretty well. So today the focus are the converging lenses. Okay, so converging lenses, otherwise known as convex lenses, because they are convex in shape. You can see here the center is thicker than the edges. It bubbles out, not in. These cause light to converge. So these cause light to converge, to meet. Diverging lenses, those are going to make light diverge. It's going to make light spread out. We'll see those in the next topic in more depth, okay? But just a brief kind of overview there. What's it look like for a converging lens? Well, these parallel rays come in, so it's going to make parallel rays converge at you guessed it, the focal point, okay? Just to take a look at why that happens, let's hop over to the grade 8 PowerPoint. Once again, taking a look here at a converging lens, a convex shaped lens. So mirrors work because of the law of reflection. Lenses work because of refraction. So they don't bounce light off of them, they let light through. So just like always, here comes a parallel ray. That green line there is the normal. See how it is perpendicular to the surface of the lens at the point of incidence, okay? Now it's going from air into glass, right? Where does light travel faster out of those two things? Travels faster in air, right? So it's going to get slowed down, which means it's going to bend towards the normal. And then it's going to do the opposite. Now it's going to go from glass into air. By the way, that dotted line, that just means it's been refracted. Okay, it doesn't mean it's virtual. I just use this in grade 8 and they don't deal with virtual. That's all. It's happening there, okay? But now it's going from glass into air. So there's another normal there, right? It's another interface. So there's another normal. Now it's going to get a speed boost. So it's going to bend away from the normal, right? And then the same thing's going to happen to this guy, and then this guy, and then this guy, and then this guy, right? So we have there a focal point, okay? And notice how that's making those parallel rays actually focus, okay? So they are actually coming together. These are real rays of light that have traveled through. So these should actually not be dotted at all. These should all be solid lines because this is real light that's traveled through, okay? They actually do converge. Okay, so just going to show you what I mean for real here really quick, okay? You might be able to see this is a converging lens, right? It's a double convex lens. So if I have it here, right? If I have a ray that enters parallel, okay, notice what happens. It enters there, gets bent towards the normal, and then upon leaving, gets bent away from that normal. Either way, the effect, so on the way in, it gets bent a little bit down, and then on the way out, it gets bent even more down, right? Because first time it's towards and second time it's away, but the angle is different. So there we go, right? Notice again how there's kind of a point that seems to be pivoting around. What do you think that point is? You bet. The focal point, right? All of the parallel rays seem to get passed through that point. Now, Important to remember that ray really is passing through the lens and then coming out on the other side. Okay, so as we get into now talking about drawing ray diagrams, okay, in terms of concepts, there's nothing necessarily new here, right? You know how refraction works, you kind of know how ray diagrams work from mirrors. Similar idea, except now we're dealing with refraction instead of reflection, okay? The same ideas hold though. So one new addition we're going to make, okay, we've always had a principal axis. Now we're also going to have a principal plane perpendicular to the principal axis through the lens, okay? So if we just go to the diagram here, this thing here, see how there's a vertical line perpendicular to the principal axis? That's the principal plane, okay? Now, what is the purpose of that? Well, we're going to assume that light only refracts once it hits that principal plane. So in other words, we are going to treat that line as just kind of the point where all of that refraction happens. Yes, really it's refracting a little bit here and then a little bit here, but for a thin enough lens, this is actually a pretty good estimation, and it makes our lives way, way, way easier. Okay, so it makes analysis much easier rather than calculating that angle of refraction on the way in, on the way out, and then doing that for at least three rays. You can imagine that's a nightmare, right? So it gives pretty accurate results for thin lenses. So just a reminder of terminology here. We have our principal axis, that's the horizontal one. Okay, that's this thing. Now, an important note on focal points. Okay, so there is going to be, in a mirror, we only had one focal point, right? That has to do with the fact that a mirror, light just hits a mirror and bounces off. So it can focus light for real, or it can appear to focus light behind, but no light can ever actually be coming from the other side of the mirror. Well, that's not true for a lens, right? Mirror light can come this way or it could come this way. So a lens naturally has two focal points, but the focal points are equal distances, assuming the shape of the lens is the same, which on both sides, which it always will be in physics 30, okay? Just a reminder of what a focal point is. A focal point is where rays parallel to the principal axis will either meet or appear to meet. So this focal point will make rays that are coming in parallel on this side meet there, right? So a parallel ray will meet there, a parallel ray will meet there. But if a ray were coming parallel this way, it would meet there, right? And meet there. So that's what the two focal points are. We call one a primary focal point and one a secondary focal point. The primary focal point is the one where light rays meet or appear to meet. Meet in the case of a converging lens, appear to meet in the case of a diverging lens, based on where your object is. Okay, so for this one, if our object is here, this would be called our primary focus or our principal focus. This would be our secondary focus because we know that light rays, parallel light rays leaving the object will actually focus there. So the principal or secondary focus is just basically decided on where parallel light rays from your object would end up focusing. Okay, quick note on the twice the focal length. So it is still interesting because it is a point at which our image properties will start to change. So beyond 2f, things will look different than within 2f. However, it is no longer called the center of curvature. Okay, so with mirrors, double the focal point was the center of curvature. That's just the property of mirrors. When you're dealing with the law of reflection, just the geometry of a circle, one of the kind of fun facts about it is that the focal point is halfway across the radius of the whole circle. But remember, refraction doesn't quite work like that. It's not just this law of reflection where stuff comes in, bounces off at the same angle, right? You could have two lenses that are the exact same shape, but if they have a different refractive index, if one's made of diamond and one's made of glass, they're going to bend light differently, right? So that's just what it's saying here. A ray of light can be bent at different angles if the lens has the exact same shape, but a different refractive index. That wasn't true for reflection, okay? So all this to just say the focal point and twice the focal point are still interesting, but the twice the focal point is no longer the center of curvature because you could have, depending on the refractive index, right? This twice the focal length isn't necessarily the center of some sphere. Okay, so to get used to our ray diagram rules for a converging lens, I'm going to switch over to paper again because, again, I think it's probably better if you watch me actually do it on paper with a ruler than to just have some ghost doing it. All right, so these are going to feel pretty familiar from our mirror rules, which makes sense, right? It's still just optics. It's just that now we're talking about refraction instead of reflection. So rule one, any ray parallel to the principal axis will refract through the principal focus. So your textbook, not all problems do this, to be honest, but your textbook will show the principal focus as F with no apostrophe and the secondary focus F with an apostrophe, okay? Just so you don't get too attached to it, I'm just going to let you know now, the principal and secondary focus are switched for a diverging lens because of the way light's going to behave. Okay, so let's go ahead and draw this ray. Any ray parallel to the principal axis will refract through the principal focus. Again, that makes sense. What is the focus? It's where parallel rays get refracted to, right? Where they meet. So parallel rays get bent. Okay. So if you saw what I did there, right? I just went parallel until I hit the principal plane. That's the vertical one. And then I just went ahead and refracted it through the principal focus. Principal meaning where do parallel rays of light end up converging from your object? Okay. Rule 2, any ray through the secondary focus will refract parallel to the principal axis. Okay, so the secondary focus, remember, what is that? Well, that's just saying where would parallel rays on this side end up converging, right? Makes sense. It would be the same as this one, just on the other side, right? The same distance, just on the other side. So I want you to think about this. This might seem weird at first, right? It might seem like a crazy rule that we're just making up, but imagine a ray came in parallel this way. You're probably okay with the fact that it would get refracted through that focus. After all, that's what a focus is, okay? Well, that just means that a ray going this way will retrace that ray's steps, right? It'll do the same thing, but backwards, okay? So what I mean by that is, let's go ahead through the secondary focus. So that's the one on this side, okay? And then parallel. Don't stress about the fact that there's no principal plane down there. That's okay. We often end up having to do this on lens diagrams. Remember, this is just a way to visualize it. The size of the lens isn't going to make any difference. What matters is the radius of curvature of the lens, not the diameter of it. Diameter just lets you collect more light. So it came in, it hit the principal plane, and then it went parallel. Came in through the secondary focal point. Now, just to show you what I mean, right? I drew that arrow there, but what if I had drawn the arrow there? You'd have no problem with that. If a parallel ray came in, it should get refracted through the focal point on this side of the lens, right? So we're just saying, well, then anything that does that backwards, well, yeah, just retrace the steps of this imaginary one that came that way, right? That's how geometry works. It has to work both ways. Now, rule 3, this should be one of your first 2 rules you use, honestly, because it's the easiest one. So again, like with mirror, you should probably do 2 and then use a third to check. This, for both types of lenses, should be one of the ones you do, not your check, just because this one's easy. This one's the hardest one to mess up. So any ray that passes through the center of the lens will come out on the other side without any refraction, okay? Now, truthfully, what happens is it just gets refracted here, but then on the other side, it's going to get refracted back the same amount. So overall, nothing, okay? So through the center of curvature, and that's our third ray. Now, if we wanted, we could put all 3 of these rules together to see how it works. So let's do rule 1. So let's just take our rule 1 diagram, add our rule 2. So any ray through the secondary focus will refract parallel to the principal axis. Let's see if we can figure out where this image is going to end up forming. Okay, so I've added rule 2. You can probably see, right? This is probably not going to be a big enough piece of paper to actually get where the image, oh, maybe, but just barely, okay? Now let's draw our, really I should have drawn this one second and then use that third one as a check, but oh well. You can kind of see that this is looking pretty good, right? Look at that. They're going to get pretty close to going to the same place. Again, we're not looking for perfection here. We just need a decent idea. So what does this ray diagram tell us? Well, it tells us that our image is going to be real. Yes, real, because these are real rays of light that are converging. That has always been our rule. With mirrors, it was a little bit easier because, yeah, when it was behind the mirror, there's no way that those could be real rays of light. But technically, that was still the rule, right? We just happen to say if the image forms behind the ear, it's got to be virtual, okay? Here, yes, it's on the other side of the lens, but that's actually where you're going to get real images because these rays of light have to pass through the lens. If you get an image over here, it's actually virtual, okay? Because real rays of light are going through the lens and they're converging here. So this is a real, okay? You can tell it's going to be inverted, and you can also definitely tell it's going to be enlarged. So same general idea as ray diagrams for mirrors, just a slight tweak that they're actually going to travel through the mirror and refract instead of reflect. Okay, let's do practice. Let's use a ray diagram to determine the properties of the image when the object distance is less than the focal length. Start off with my principal axis, then add a principal plane, and we're doing a converging lens. Now this part is important. You do really need to make sure, okay, that your focal points are equidistant on either side of the mirror, okay? So how about I'll do 4s. So 4 centimeters and then 8 centimeters for the 2F, okay? And then I'll do the same thing over here. So 4 centimeters. So this is going to be the secondary focus because the object I'm going to draw on this side. So parallel rays of light are not going to converge or appear to converge there. Okay, they're going to converge or appear to converge here. All right, well, they're going to actually converge there. So when DO, when the distance of the object is less than the focal length, so this is the focal length from the vertex to the focal point or the secondary. There's my object. Let's go ahead and do rule 1, parallel and then through the focal point or the principal focal point. Okay, hits the principal plane and gets bent towards the focus. Now, I'm going to go ahead and extend this one back because I know how this is going to go, but you can always go back and do this after if you realize, okay. Yes, the real ray of light went this way, okay, but you can imagine if our eye was over here, what would it think? It would think, well, there's a real ray of light hitting me, but it seems to have come from over there. Sometimes that's going to be where the image forms, sometimes not, okay. I'm actually going to go ahead and do a rule 3 next. That's the easier one, the simpler one. So you should use it to find it, and then the other one as a check, okay? So then through the center and no refraction, straight on through, okay? Now, you might be looking at this, okay? Now, if you hadn't drawn that dotted line, which I would forgive you for, we're just starting this, right? You might be noticing, these two are never going to converge, okay? And you'd be right, but check back here, right? Look at that. These two, they can appear to converge behind the lens. So if you're over here, you're now saying, it looks like these 2 rays of light that left this object seem to be coming from here. Okay, let's check with our third one. So again, since we're just retracing the steps anyway, right? What would a parallel ray on this side do? It would come in parallel. It would get refracted through that secondary focal point. So let's just retrace those steps because along the way, it would have to go through here, right? So we can still retrace the steps by doing this. So a ray leaves, hits the principal plane, and gets refracted parallel. But you might see where this is going, right? If your eye's over here, if you have a big eye, right? What's going to happen? Your eye is going to trace that ray back to here. And voila, look at that. They all meet at the same place. So here we have a image. Okay, so that's our image. Now, question, what kind of rays converge to make our image? Are they real rays of light, right? Are these real rays of light that are actually intersecting? No, right? These are just the projections of real rays of light back. These are virtual rays. So virtual rays are converging, not real rays of light. This is a virtual image. Quick tip for lenses, okay, a way to check as you go. Understand that, but a quick way to check. If the image forms on the same side as the object, it is virtual, okay? It kind of has to be because how could rays of light leave this object and then actually end up converging over here? There's no way, right? They're on their way out from the object through the lens. There's no way for them to actually converge there. So it's kind of like the opposite of our mirrors. With our mirrors, if the rays seem to converge over here on the other side of the mirror, it was always a virtual because how could rays be converging behind the mirror? The mirror behind the mirror isn't even a real place, right? Whereas here, if they appear over here, it's probably real because then real rays of light are actually converging. Okay, so the opposite. So it's virtual, definitely enlarged, and it's upright, right? It's erect. Okay, let's try another one. Ooh, what if the object distance is the focal length? Any guesses? If you're saying, I bet no image is formed, great, you're right. Because, remember, focal length, the focal point is where parallel rays meet or appear to meet. So if rays are leaving from that point, well, they're going to do that backwards, which means they're going to go parallel. And if they go parallel, they can never meet, they can never focus, and so no image will be formed. Okay, so there's my principal plane and principal axis. Secondary focus, twice the secondary focus. Primary focus, twice the primary focus. Okay, so when the object is at the focal length, or when DO is equal to the focal length, let's see what happens. So remember, what is the focal point? It's where rays converge or appear to converge. So I'm going to go ahead and draw our rule 1. So rays parallel to the principal axis, okay, hits the principal plane and goes through the focal point, just like any other parallel ray would do. Okay, now what about another ray that leaves there and goes through the center? Aha, look at this. You can already kind of see it shaping up, right? So another ray that leaves there, to form an image of this top of this arrow, they will need to meet somewhere. But look at that, right? Pretty parallel. Well, very parallel, perfectly parallel, okay? So what do we know about parallel lines? They never meet. So these will never meet. An image of that will never form, same as a mirror, okay? Because that's what a focal point is. It's where parallel rays meet. So if you rewind that and go from the focal length, you're going to end up going parallel. Before I wrap this one up and go into the examples video, I'm just going to quickly give an overview of the math, okay? It's actually the exact same two formulas we used with mirrors. So 1 over F equals 1 over DI plus 1 over DO, and M equals HI over HO equals negative DI over DO, okay? In fact, the sign convention is actually technically the same, though you probably will have to do a little bit of more thinking here to wrap your head around it at first. So this was true with mirrors. Real is positive, virtual is negative, okay? And this includes virtual focal lengths. So when we get into diverging lenses, you'll see what I mean, okay? But for now, were rays really focusing at the focal point for a converging one, the ones we were just looking at? Yeah, they were, right? They really were focusing there. So converging lenses have positive focal lengths. Diverging lenses are going to have negative focal lengths. As we'll see, they only appear to focus rays, and so that is a virtual focal point, but that's for next topic, okay? And just like before, erect is positive, inverted is negative. So again, if virtual rays are meeting to produce your image, DI is negative. So converging can produce real and virtual. I'll show you what I mean here in a sec. Convex, converging lenses, just like converging mirrors, are a little more complicated. You can get real images and virtual images. Real in this case will mean, okay, if we're looking for a simple look at it, real images for lenses, they form on the opposite side of the lens as the object, right? Of course they have to, because that's where the real rays are going to be. The only way to get a real image is if real rays converge, right? Real rays are not converging on the same side as the lens, as the object is. Whereas virtual is going to mean, okay, you guessed it, right? If it's virtual, it forms on the same side of the lens as the object is, because that's where virtual rays might appear to converge once our eyes kind of trace them back. So just going to play around with a converging lens here with you a bit, just to kind of show you before, and then I'll go to the other video and do the actual examples here. But I just want to show you a converging lens in action. Okay, so I have here a double-sided convex lens, right? See how it's bubbled out on both sides? So a converging lens, okay? Now, I can put my object, which is my eye, right, very close. What do you get? You get an enlarged erect image, okay? Now, as we saw in our ray tracing diagram, this is a virtual image, so you could not project this image on a screen. As you go away, it gets bigger, it gets bigger, it gets bigger. Look what's happening about there. Notice how it's kind of just garbage, it's kind of just gobbledygook, right? That means, where do you think we are? Well, we're probably at the focal length, right? Then what did we see when we went beyond the focal length? We saw we now got a real image enlarged but inverted. See my eye? Inverted. Okay, and then if I keep moving, okay, it gets smaller and smaller and smaller. Once I hit twice the focal length, it becomes the same size, and then beyond that, okay, and then beyond that, it's smaller. I just realized I have to move myself. If I move it to you, I'm making it so you're seeing it from within the focal length. So that messes with things too, right? Lenses have two focal lengths, right? So there we go. Okay, now it is inverted but diminished. I'm beyond twice the focal length. At twice the focal length, it should be about the same size. At the focal length, you get garbage, right? See how it's not focused at all? No image is being produced. The rays that are leaving are getting sent out parallel, right? And then within virtual, enlarged, but upright, okay? How do I know those images are real? Why should you believe me that they're real images? I actually haven't shown you a projection yet. It's hard to do with the mirrors. Okay, I couldn't really do it very well with the mirrors, but I can do it with a lens. So I just have here a flame, okay? Now, if you look on the board behind, notice right now it's not very focused, okay? But if I change the object distance, okay, I don't know if you can tell on the video, but it becomes very focused there, right? I get a clear, inverted, real image. Why real? Well, it can be reproduced, right? That's a real image on the board there because rays of light really are converging from the flame, right, to be projected onto the board and reproduce the image. Or how do I know within the focal length is virtual? Well, if I go in, right, no projection anymore. The rays aren't actually converging. They appear to converge from the other side. So for you, if you're looking at it, they appear to converge and you can appear to get an image, right? And it's even enlarged, as you can see there, right? But that's not real light rays like they are when we get beyond the focal length. And we can actually reproduce the image. Inverted, enlarged, real. So again, just to drive it home, okay, convex converging lenses have positive focal length because light really is converging there, right? We are really able to project it. Real images are formed. So just like before, real is positive, virtual is negative. There's just a little more thinking going on here. Okay, I'll do the examples on the next few pages in another video. If you want, you can go check those out. Otherwise, if you're just looking for practice, check the Google Classroom or the agenda for which problems go with this stuff.